Several thousand meters beneath the Red Sea, explorers encountered something that challenged one of the simplest assumptions about water, that it always mixes with water. Instead, their cameras revealed what looked like the shoreline of a hidden lake resting on the seafloor. The boundary was so sharply defined that it reflected light almost like polished glass. It looked as though a diver could swim across the surface of an underwater lake. Yet this was no illusion. Two bodies of water were occupying the same place while refusing to become one. At first, the discovery raised a practical question rather than a philosophical one. If everything below the surface is already ocean, what could possibly create another lake underneath it? The answer wasn't a solid barrier or an underground cave. It was chemistry. The water inside these strange basins contains such extraordinary concentrations of dissolved salt that it becomes dramatically denser than the seawater above. Much like thick syrup settling beneath ordinary water, it sinks into natural depressions instead of dispersing, forming a distinct body of liquid with its own remarkably stable shoreline. That explanation solves only part of the mystery. Dense water should still gradually mix with its surroundings, eventually disappearing. Yet some of these pools have persisted for immense spans of time, suggesting an active process is constantly maintaining them. They are not ancient puddles slowly fading away. They are living geological systems that continue to renew themselves even today. And once researchers began tracing the source of that hidden supply, they discovered the story had begun millions of years before the first underwater expedition ever descended into the darkness. The answer to the mystery wasn't hidden inside the lakes themselves. It was buried thousands of meters beneath them. Deep below the seafloor lies an enormous layer of ancient salt that, despite looking as solid as stone, behaves in a surprisingly different way. Under immense pressure, it slowly flows, almost like a glacier moving so gradually that an entire human civilization could rise and fall without noticing the change. Even today, that invisible movement continues beneath the Red Sea. Its story began millions of years ago, when parts of the region were repeatedly cut off from the open ocean. Powerful evaporation removed vast amounts of water, but every dissolved mineral remained behind. Over countless cycles, thick layers of salt accumulated across the ancient seabed. As younger sediments buried those deposits, the salt began to bend, creep, and reshape the surrounding rock. That slow movement fractured the seafloor, opening hidden pathways that would eventually transform the landscape above. Those fractures became natural conduits. Seawater gradually seeped downward, dissolved the buried salt, and turned into an exceptionally concentrated brine. Heated deep within the earth, the dense fluid slowly rose back toward the seafloor, continually replenishing the strange lakes above. The discovery changed how researchers viewed these pools. They were not isolated bodies of water left behind by some ancient event. They were part of an active geological system that was still operating. The evidence became impossible to ignore. Some pools even overflow, sending dense rivers creeping silently across the seafloor before spilling into deeper basins. Following those hidden currents would lead scientists to an even greater surprise, because where those chemical rivers ended, a place that should have been lifeless was unexpectedly full of life. The shoreline of these underwater lakes marks one of the sharpest environmental boundaries on Earth. From a distance, nothing appears unusual, but for an animal drifting only a few centimeters too far, crossing that invisible line can become a fatal mistake. Cameras have captured fish approaching the edge with apparent caution, as though sensing a danger they cannot see. Some turn away just in time. Others disappear into the dense brine below and never return. It is a boundary that separates ordinary seawater from conditions where most familiar marine life cannot survive. The reason is hidden within the water itself. Inside the pool, oxygen is almost entirely absent, while dissolved salts reach concentrations far beyond what most marine animals can tolerate. Chemicals such as hydrogen sulfide and methane further transform the brine into an environment hostile to nearly all familiar ocean life. Animals that descend into it quickly lose the ability to swim, sinking deeper into the dense liquid before dying. Because decomposition is dramatically slowed, the remains often persist, creating a silent shoreline that has become both a trap and a remarkably preserved record of the creatures that entered it. Yet this apparent graveyard forced scientists to confront an even greater contradiction. If the pools are so deadly, why do expeditions repeatedly find thriving communities gathered around their edges? Crabs patrol the boundary, shrimp swarm across nearby sediments, predatory fish linger above, treating the shoreline as a reliable hunting ground. At first glance, it looks like a place where nothing should survive. In reality, researchers had been looking in the wrong place. What first appeared to be a lifeless chemical wasteland was, in fact, supporting one of the most unusual ecosystems in the ocean. The answer lay not inside the toxic water, but along the razor-thin frontier where ordinary seawater meets the rising brine. At that boundary, chemicals escaping from deep within the earth become an unexpected source of energy, one capable of sustaining an entire food web without relying on sunlight. That discovery would ultimately overturn one of biology's oldest assumptions and reveal that life has more than one way to power a world. Everything scientists had seen so far pointed toward a contradiction. The shoreline of the brine pools supported a surprisingly rich ecosystem, yet sunlight, the foundation of almost every familiar food chain, had never reached these depths. Very little organic material drifted down from the surface. By every conventional understanding of biology, this ecosystem should not have had enough energy to survive. The breakthrough came only after researchers stopped looking at the larger animals and focused instead on the microscopic life coating the rocks and sediments. There they found something extraordinary. In complete darkness, these tiny organisms were producing the organic matter that supported everything living around them. An entire food web existed without depending on a single ray of sunlight. Only after scientists understood this remarkable process did they give it a name: chemosynthesis*. Rather than capturing energy from the sun, these microbes drew it directly from chemicals such as methane and hydrogen sulfide rising with the mineral-rich brine. In effect, the Earth's own internal chemistry had become the engine powering life. That realization reached far beyond the boundaries of the Red Sea. It challenged one of biology's deepest assumptions. Perhaps sunlight was not the universal requirement for complex ecosystems after all. Places once dismissed as too dark, too toxic, or too chemically extreme suddenly appeared far more promising. Instead of asking how life had adapted to an impossible environment, scientists began asking how many other environments like this might still be waiting to be discovered. The implications extended even further when researchers compared these pools with conditions on the early Earth. Billions of years ago, our planet contained little oxygen, intense volcanic activity, and oceans rich in dissolved chemicals. What first seemed like an extraordinary exception now looked surprisingly familiar, a surviving window into a much older world. And if chemistry alone can sustain thriving ecosystems beneath Earth's oceans, then hidden oceans elsewhere in the solar system may deserve to be viewed in an entirely new light. By the time researchers understood how these brine pools functioned, they had begun asking a far more profound question. Instead of wondering how such unusual lakes could exist, they started asking whether environments like this had once been far more common. Although the pools are not exact replicas of the early Earth, they preserve several conditions believed to have existed billions of years ago: oxygen-poor waters, abundant dissolved chemicals, and ecosystems sustained without sunlight. Rather than revealing where life began, they offer one of the closest natural laboratories for exploring how the earliest living systems may have survived and evolved. That shift in understanding reached far beyond the Red Sea. For decades, the search for life elsewhere focused primarily on finding places that resembled the surface of our own planet, worlds with sunlight, liquid water, and moderate conditions. The brine pools challenged that assumption. Here was a thriving ecosystem powered not by sunlight, but by chemical energy rising from deep within the Earth. If life can flourish under those conditions here, then hidden oceans beneath the icy crusts of moons, such as Europa and Enceladus, become far more compelling places to investigate. Their frozen exteriors may conceal environments where water, rock, and internal heat have interacted for millions of years. Scientists remain careful not to treat that possibility as evidence. No discovery in the Red Sea proves that life exists elsewhere. What it has done is reshape the questions, guiding one of humanity's greatest scientific searches. Instead of looking only for worlds that resemble Earth at the surface, researchers are increasingly searching for places where the underlying chemistry could make life possible, even in complete darkness. Perhaps that is the most remarkable legacy of these hidden lakes. A discovery that began with what appeared to be an impossible body of water beneath the sea ultimately changed far more than our understanding of one remote corner of the ocean. It expanded the boundaries of where life might exist, revealed new ways that ecosystems can sustain themselves, and reminded us that some of the most important clues about our place in the universe may still be waiting beneath landscapes we once believed we already understood.